So this is our Rube Goldberg project. Our goal was to blow bubbles. We first started out with a counterweight. So what we did is we would pour water into this cup, which then would set off the weight, which would release a ball to the Newton's cradle, which then would hit the sorry piece, which would go down the ramp, which would eventually hit the marble down the tube. It would then be released into projectile motion and knock down the Jenga blocks in sequence, which would then use energy to release the car down the ramp.
After the car went down the ramp, it would hit the stopper to release the seesaw, which would then have the balloon float all the way up here to hit the chopsticks. And the chopsticks would release the counterweight on the ball, and the ball would roll down into this cup sitting on the cup diving board, and the cup would slide down the zip line into the on switch of the fan, which would then blow the bubbles.
Newton's first law of motion states that an object will stay at rest unless acted upon by an unbalanced force. Similarly, an object in motion will remain in motion unless an external force acts upon it. This law is also referred to as the law of inertia. What Newton's first law is basically saying is that the objects behave as expected. In our project, this law is shown with the use of the Jenga blocks as dominoes. The blocks remain at rest with no velocity or direction until the flying marble collides with the first block, applying a force. Newton's second law of motion states that an object will accelerate when acted upon by an outside force. This is shown in physics by the equation, the sum of the forces equals mass times acceleration. This is evident in our project when the balloon is held to the ground by the tension force in the string and the force of gravity. When the tension force is removed, the upward thrust due to the helium causes the balloon to rise, despite the force of gravity acting both before and after.
Newton's third law of motion states that for every action there is an equal and opposite reaction. What this means is that pushing on an object causes that object to push back against you the exact same amount, but in the opposite direction. For example, when you are standing on the ground, you are pushing down on the earth with the same magnitude of force that it is pushing back up at you. This is shown in our Rube Goldberg machine when water activates the counterweight system in step 1. The cup is balanced on the rod and has an equal balance on the other side. When the cup is slowly filled with water, the cup's mass increases, causing an increase in its acceleration due to gravity. As a reaction to this, an equal and opposite force is applied to the other side, causing the other side to rise. This step pictures an equal and opposite reaction.
Energy is the ability to do work. The law of conservation of energy is a principle that states that energy cannot be created nor destroyed, but can be altered from one state to another. This is prevalent in our machine by the use of the zip line. The cup is resting on the so-called diving board, elevated about 4 feet above ground level. The cup has the potential to slide down the zip line, so it has potential energy, since it has the potential to do work. As the ball is activated and falls into the cup, it releases the cup down the zip line to activate the fan and blow bubbles, accomplishing our task. At this very moment, potential energy is transformed into kinetic energy, because the cup now has velocity and is moving and is losing altitude.
Momentum is the force of objects in motion. The law of conservation of momentum states that everything that moves has momentum equal to its mass times its velocity. Like energy, momentum is conserved. It's adequate to understand that momentum is a vector quantity, meaning that the direction of the force is an important factor when determining the momentum. This principle is a direct consequence of Newton's third law. In our project, the Newton's cradle is demonstrated when the first ball is released. When the first ball collides with the second ball, it's traveling in a specific direction, which means the momentum is also moving in this same direction. Any change in direction would result in a change in momentum. However, this is impossible without the influence of an outside force. This is why the first ball does not simply bounce off the second ball. The momentum carries the energy through all of the balls in the same direction.
Please, why?
You didn't reset the car.